Let's look at the finite well. So we still have a potential which is V naught. This is x equals 0. X equals 0. And this is x equals L. So it's V naught everywhere except in here where it's 0. So that's the value of the potential there. But we want to consider states that have an energy, E, that is greater than V naught. So, right, we have this region here, the region x less than 0, the region x greater than L, and the region between 0 and L, so region 1, region 2, region 3. And the solution, right, the energy eigenfunctions have the following form. We have, well, they all have the same form because E is greater than, E minus the potential always has the same sign, it's positive. So we have e to the I kx in all cases, but here in region 1, it's e to the I k1x. We also have a solution with a minus sign, and k1 is the wave number, e minus v naught over h bar squared. In region 2, the solutions are same as these two, but with wave number k2, where k2 is 2me over h bar squared because the potential is 0 there. And in region 3, we have coefficient e to the I k1x again. And the asymmetry between this solution and this solution has to do with, we're not in the situation where the energy, where the particle is bound, and so there's no symmetry between these two regions. We have a reflection and transmission possibility, and these coefficients have to capture that. So there's some asymmetry between these two solutions. Of course, we have continuity. So the continuity of the function at x equals 0 gives us x equals 0, e to 0 is just 1, so we get a plus b. That has to be equal to this function at x equals 0, and so that's c plus d. The continuity of the first derivative at x equals 0 gives us I k1a times this evaluated at x equals 0 minus I k1b is equal to I k2c at x equals 0. Again, that's 1 minus I k2d. At x equals L, we have So these are x equals 0 boundary conditions. Now we'll do x equals L boundary conditions. This function has to equal to that function, so we have c e to the I k2L plus d e to the minus I k2L. That has to equal to this function here. That's equal to e to the I k1L. And then the first derivative of these functions gives us I k2 c e to the I k2L minus I k2d e to the minus I k2L, and that has to equal to I k1 e to the I k1 L. And so these are the boundary conditions at x equals L. And so we notice that we have 4 equations. And 5 coefficients, for 5 amplitudes here. And so we can determine the amplitudes in relation to the to one of them, right, the amplitude A. And then notice that we don't get a condition on the energy. So we can conclude that the value of E is not constrained. Right? So E can be a continuous quantity.